1 minute before. I was trying to see how many participants we've got. 18, okay. Maybe a few more will come. $20. Okay, that's a nice round number. And it's less than a minute before the time. So maybe I can go ahead and start with my introduction. Welcome to the Colloquium series, first Colloquium of the fall. Rainer, do you want to say a few words in terms of a welcome?
Welcome to the Colloquium series. I don't know if you can hear me in Hawking, but yes, it's going to be a little bit different this semester, but hopefully everything will go fine. And we have, I think, a good speaker to kick this all off.
Okay, so please load up on cookies and coffee and fruit or whatever other favorite snacks you have, and let's start. It's my pleasure to introduce Alexey Akimov, our own, based here in College Station for 5 years now. And he'll talk about his own work in these most recent 5 years. And as a means of introduction, I want to talk a little about his career before coming to Texas A&M. Alexey graduated from one of the best and most famous schools on the other side of the Atlantic, Moscow Institute of Physics and Technology. In fact, he got 3 degrees from that famous school, a bachelor's degree, a master's degree, and a PhD. And then he stayed in Moscow working at the famous Lebedev Institute, and then transitioning from there. Well, he spent time on this side of the Atlantic at also a reasonably well-known school in Boston called Harvard University. Then went to work for the Russian Quantum Center, where he was an acting director and also a principal investigator. And his work during all those years is best characterized by the word single. Well, he started his physics career by working with cold atoms, but then he added to his repertoire every technique that had the word single in it. We all know and love single photons. We know how to detect single photons, and he does too. But he also works with single atoms. He has put a single atom into an optical cavity, and quantum dots, spins, and even a plasmon. There is this paper where he showed that he can produce and detect single plasmons. Let's see, what else do I need to say? Maybe in terms of awards, I noticed that among several of his awards, he has a Vavilov Prize back from the time at the Lebedev Institute. And for those of you nonlinear optics students who are here in the audience, I remind you Vavilov was the grandfather of nonlinear optics, performing the first nonlinear optics experiment in 1925. In a few years, we can celebrate 100 years of nonlinear optics. So that's the name attached to the prize Alexey received. And here at Texas A&M, in addition to the work in the lab that he'll be talking about himself, I know, and many of you know, that he's been very active in our physics and optics community, an active participant in all possible festivals, and a leader when it comes to seminars, AMO seminars, OSA seminars for optics students. He's been participating and helping to run some of those. And obviously, yeah, working with undergraduate and graduate students in his lab. I think I can stop here and let Alexey talk more about his research.
Thank you, Alexey. I now feel very single here, but I guess I will talk about my work. So my work is motivated by main idea of quantum technologies, which is very popular these days. And let's see if my pointer is fancy enough to work. Yeah. Good. Okay, first technical details. Y. And yeah, it's now working. Cool. So first thing I will be talking about is our work with diamond. And for those who don't know what diamond is, I have a diamond. So that's the diamond. That's of course model. So each of these black lines is just 1.5 angstroms in real life. But it does contain all you need to know about diamonds. So it has this nice honeycomb structure. You can see in some directions through it. It's very hollow structure. And it also sometimes have defects. So here it's indicated with this red, I don't know if it's seen on Zoom, and blue inserts. So basically you can replace one of these carbon atoms, each node represents here carbon atom, with something else. And in diamond, very often, you also get a vacancy nearby. So if this atom with, say, nitrogen, nearby, like blue will represent absence of the carbon. So you have something like a molecule, something which has access associated with it. And that is in a matrix which is more or less neutral. It's optically transparent. Diamond is transparent in a very wide range. Band gap is around 5 electron volts for specialists. And diamond is naturally quite pure material. It doesn't have many impurities. So you really can isolate single impurity and work with a single one. And that's what making it interesting for quantum information. You can work with a single atom, which is inside solid state, which is inside some material you can have in your hands like I do, right? You can just take it in your hands and rotate it. So what do we want to do with these colocenters and diamonds? Well, our general motivation comes from like industry. So we're thinking that in principle, if we're thinking about modern computers and modern internet, there is a limitation coming from the fact that we're using electrons to transmit information because there are ohmical losses associated with those. And if we instead will use photons, photons don't have ohmical losses. They also have bigger carrier frequencies, so you can modulate them in high frequencies and possibly transmitting a signal. You can also think about using individual bits to actually build computer and build quantum computer instead of classical one. But the problem is that if you want to use photons, then you need somehow to switch photons with photons. If you switch photons with electrons, you don't really win much because you still have ohmical losses for each switch. So this picture I really like a lot. This is first a picture of optical processor from IBM, which appears, and I think still is on the site of IBM, and it appeared there something like 7 years ago. And I thought, like in a couple of years, we will buy it, and there is no need to work in the field of photons and do optical processors. And it never happened, so I started to work in the field of optical processors. And then I met the guy who made this picture, and he said, "Oh, don't worry about it. It's a DARPA project which never was supported." Picture is still on the website, but why it never was supported? Well, because there are these switches here, these yellow, barely seen boxes, are switches which switching photons with photons, and there is no such a thing in the industry. So this was a nice project, but it required much more scientific development. And how can you switch photons with photons? Well, normally photons do not interact. We know that if you try to interfere to laser beams or to any kind of photon beams. They just go through each other and have no information about each other after they pass a region in which they interfere, right? So there is no interaction, it's just zero. So you need to develop somehow some mechanism how two photons can talk with each other and not involve electrical current. And of course, if you can do it, if you can make photons talk, then there is more than one application. You not only can build an optical computer, you not only can build something like a quantum computer, you can also think about communication, because in communication we already use photons everywhere. Most of our internet is on optical fibers. But there is more to that. We can, if we use single photons, we can use so-called quantum communication, where we use the fact that you cannot copy a single photon without introducing noise to introduce new level of security. Right? So if somebody copies you, you will know because you will have more noise. And that's very nice technology. It's available on market already for probably 10 years. Nobody buys it, and the reason why it doesn't really work from here to Houston. It doesn't work for him to Houston exactly for the same reason. You cannot amplify your photon, and it turns out even in optical fibers you're losing photon in few tens of kilometers. So if you have 150 kilometers from here to Houston, you just have zero probability to have single photon pass from here to there. And you cannot amplify, because if you amplify, you're trying to copy your photon, so you screw your security. So you need to develop something else. You need somehow to develop algorithm in which you can connect two photons on a large distance through some intermediate memories, which will be quantum secure, and that scheme is known. But one needs somehow to be able to map photons to some kind of solid state memory to actually, process all this memory. So it turns out you can also make photons interact through matter, because photons do not interact with each other, but they do interact with matter. They could absorb, they could be re-emit, they interact with matter, and you can use some matter to mediate this interaction. So just one example, so you can see how it could happen. If I have one-dimensional structure, doesn't matter what the structure is, but I have conditions that my photons are localized to the structure and interact with my atom sitting nearby with probability of 100%. Then if I send photon in the structure and it's resonant with an atom, it will be exact. It's just like mathematical fact. You can do calculations, you will find that that's what happened. So now if you have 3-level atom, most of the atoms have more than 3 levels, and you have some transition with which your photon is resonant, and you, with help of other photons, can do something like Raman transition and move your atom to another state, then when you apply photon, it doesn't really see your atom anymore, and it goes through, right? So by just like applying a couple of photons to switch your atom, you can change reflectivity of the system. You can make photon go through, or you can make photon be reflected. That's basically switch, right? And switch is basically basic element for any circuit. You can also call it transistor, because you can actually, with just a couple of photons, switch many photons. So you can have amplification. So once you have a device like that, you can build already many things. Now, what is the problem? So let's just build this device. Well, the problem is that usually when you try to focus light on an atom, you're not really succeeding, because either the atom is not localized well enough, or your light is not localized well enough, and probability of interaction is usually small. So normally you have atom sitting somewhere and like purely focused light on it, and then probability of interaction is something like cross-section of an atom, lambda squared divided by your beam diameter, and you maybe can get to a few percent, but that's as good as you can do in realistic experiment. So what people figured, you can actually put mirrors around your atom, and then your photon will have more than one attempt. It will go through, reflect, go through, reflect, and probability of interaction will be enhanced by something like fidelity of the scale. And then you can actually make interaction probability 1 for atom. Here I considered absorption, but the emission is just inverse process of absorption. So if you have atom in a cavity like this, it also will emit inside the cavity with probability close to 1. So it's really will be a system which is strongly integrated with light. Now, I said we're working with diamond. What specific color centers do we work with? There is one color center which is very famous. It's a nitrogen vacancy color center. So it's like one of the carbon atoms is replaced by nitrogen, another is just missing carbon. And it turns out that for stability, like energetically, it's more favorable to have extra electrons. So it's actually negatively charged ion inside the diamond. And this color center has many important results associated with it. So it's room temperature quantum memory exceeding several seconds. It has quantum register, which could be done in a room temperature, etc., etc. But it's also very good sensor. It senses electric field, magnetic field, and it senses electric field very good because all electron density is concentrated on a vacancy, and nitrogen is kind of positively charged ion there, so it's polar structure. It's polar structure already. It has dipole moment. It senses it senses electric field very well. But that means that if you're trying to do some kind of cavity around this structure, trying to do some nanostructuring around this color center and creating some defects which may be charged and they create electric field, this thing will sense them. And in the first experiment people done with a nitrogen vacancy color center, they kind of built some cavity around it. They were not able to find resonance line of this color center at all. So big distortion was created. So it's very nice, but it's a little bit too sensitive. So we need something, if we want to, like use some nanostructures, and we definitely don't want our cavity to be huge, it needs to be small. For our diamond, we need different color center. So first idea was to use a silicon vacancy color center. And the idea is that if you have silicon actually big atom. It's bigger than a carbon. It's under it in a Mendeleev table, and it just doesn't fit in the position of the carbon. It's too big. So what it does instead, it sits in between two missing carbons. And that structure is symmetric. Now you have electronic cloud on top, electronic cloud on the bottom. They have symmetry, so it's not sensitive to linear approximation to the electric field, and therefore you can hope the structure will behave better in a solid state, in some nanostructure, where there is a lot of defects around. It turns out this structure indeed does that, but it has another problem because of specifics of this silicon color center. This structure emits on a wavelength of around 740 nanometers, and that's long enough wavelength for optical phonons to create decay of excited state. So excited state of this color center is decaying mostly not through photons, which we want to work with, but through mechanical oscillations of a diamond structure. And only 5% go into light, and 95% goes to basically heating of your sun. That's not very well. So what we want to do, we want to shift our wavelengths towards shorter wavelengths, so optical phonons cannot release excitation of our color center. And it turns out if you just go down in the Mendeleev table, go to germanium vacancy color center, that happens. It's again huge color center. This is not our work. I don't really know how this picture is supposed to represent same as this one, but that's presumably the same structure. Germanium also has symmetric color center, but it emits in 602 nanometers, its visible range, and it does emit mostly radiation. It turns out that other color centers which are sitting under the germanium are as good. So if you take a tin or a lead, they all emit around 600 nanometers, so they're all good. The problem is they're getting bigger, bigger, and bigger, and germanium you can grow in a growing machine with a color centers inside. Starting from a tin, it just doesn't fit in diamond structure anymore. So if you try to do growing, diamond just rejects in and everything under. In the Mendeleev table, so germanium is kind of like optimal choice, but if you do implantation, you still can do something below. Now, what kind of nanostructure, what kind of cavity should we make? Well, before answering this question, we should understand how cavity interacts with the atom, and since it's colloquium, I will remind it. So basically, if we have a photon in a cavity and we have an atom, we can describe interaction between them by coupling strength, which is the product of dipole moment to electric field, and we need to divide to a Planck constant if we want something on a frequency scale. Electric field of single photon in a cavity we can calculate if we know that it's just one photon and we know volume of the cavity. That's basically an example from a quantum mechanics book. And then it turns out that parameter which characterizes how strongly photon atom actually interacts with photon in a cavity is 2g squared divided by kappa gamma, where kappa is how fast photon decays from a cavity and gamma is free space decay rate, because photon, of course, can still escape in a free space. So what happens when this parameter is bigger than 1? Well, that means that if atom emitting a photon, it's starting to see this photon before a photon escapes the cavity. And this emission process affects atom backwards. That's what people call strong coupling. So basically, at this moment, you cannot separate atom and a cavity anymore. Atom, once it's starting, to produce a photon, it sees the cavity, and it's now a system which should be considered as a whole. And that's what we want. We want atoms strongly interact with the photons in our cavity. Now, it turns out that you can convert this parameter, this cooperativity, to something like Q factor of the cavity divided by mode volume, which is measured in a wavelength. People often use this parameter because it's much more convenient. You just, you calculated Q factor, calculated mode volume, voila. The problem is that, of course, there is a prefactor about which people often forget. First of all, a wavelength should be in a wavelength should be calculated inside the media, not in a free space, and it's a little shorter wavelength. So your volume actually need to be much smaller than you might think. And there is also a prefactor which is about 1 over 10. So actually, like when you say Q over V, you need to be a little bit careful. It's not just like Q over V is equal 1 is enough. It actually need to be more than 10. And you also need to take into account that wavelengths need to be in the media. Now, there are plenty of cavities people trying to use for similar purposes. One is just like bulk Fabry-Perot cavities, which is to try to put two mirrors, move them close to an atom, and try to make a cavity. That happens to be very bulky, even though lately people figure out that you can do it with optical fibers and do really tiny cavities with the fibers. And right now, that's actually a very interesting approach. And another side, you can try to use plasmons, just have metallic wire in which you have a analog of photons, plasmas propagating on the wire and build cavity out of it. You can have very nice localization in metallic wires. You can have really small volume, but your Q factor is limited. It's usually not more than 100 because wire is metallic, so you have chemical losses again. Even though it's a photon, like it's analog of photons, there is still associated electrical current in the wire because metal has conductivity, and that leads to a lot of losses. So this is probably the most compact way, and the ratio is interesting, but it's associated with some heating, and like eventually we decided that's probably not the good way to go. There are also microtoroids, which are nice technology, can give you very, very high quality factors. Probably it's a record of all cavities. It has rather large mode volume, but still the ratio is actually great. The problem with this cavity is that because it's so big, distance between the modes is very short. And solid state emitters such as a germanium vacancy color center, they have rather broad line, which is like 100 nanometers or something like that overall. And you only need something narrow from this line, some resonant transitions. The rest you kind of don't really want to enhance. So it's doing a little bit too much. It enhances everything, and you don't necessarily want it. So photonic crystal cavities are somewhere in between. They have very nice Q factors. They have decent mode volumes. They're as small as 1 wavelength cube. So that's very good ratio. And they have still, that could be single mode cavity. So you have like 1 or 2 modes per whole range of wavelengths. So we decided that that's probably optimal, and that's the way we want to go. Now, of course, other people trying to work in this direction too. And for example, people try to do cavities directly in diamond, and that's in a Harvard group where I worked before, and I seen this thing done. And that's exactly where it happened when people were not able to find nitrogen vacancy color center in this cavity once they made the cavity. They can see it room temperature, they cool it down to see resonance lines, and they just cannot find them. So it's too sensitive to defects created. And during the fabrication, they tried to do a step forwards. They put, instead of a nitrogen vacancy, silicon vacancy, and that worked much better. They already seen some coupling to the cavity and reached some strong coupling regime. And of course, there are many other groups which are working along similar lines. So question is, what can we do on top of that? Well, what we can do, we can try to go to more industry-friendly materials, because diamond is really hard to work with. It's very hard material. It's hard to fabricate. So we can try to combine some cavities made of more common material with nanodiamonds, which can lithographically put on top of our cavities, and then we can probably win in Q factor, because our cavity will be just done on material we can better process. We can still have all advantages of having germanium vacancy color center, and that might be more beneficial. So problems is we need, of course, to have this good nanodiamonds. So we're collaborating with growing groups. We need good cavity. So we were trying to collaborate with some people who doing good materials for cavity. And we need to know how to position diamonds. But by the time we started, we already knew how to do the positioning. I will show one slide on that. So what kind of cavity should we take? Well, we're doing photonic crystal cavities. They called photonic crystal because they have periodic structure. So they have holes which periodically repeat each other. And much like in solid state, if you have periodic structure, you expect wave function to be periodic, and you expect to have zone structure. So for some wave vectors, for some energies, you will have allowed zone, you will have valence zone, and you will have some band gap. So some range of frequencies in which light just cannot propagate through the structure. You can also think about it as a mirror. So basically, it's a dielectric mirror which has many layers of dielectric with a quarter wave thickness. And if inside this structure, somewhere, let's say here, let's see if I can do it. Yeah, I can put that, just remove one of the holes, then I have two mirrors on two sides. Right? So light cannot propagate in certain frequencies through these mirrors, it will stuck on this hole. Now, it turns out that you don't have to really remove the hole here. What you can do, you can change shape of your cavity a little bit, just slightly. Here it's like small parabolic change of shape, and that's enough to emulate the effect in the center of the cavity, and that happens to give you higher Q factor of the cavity. There are two ways how you can do it. You can just change thickness or change size of the hole. They're somewhat equivalent. There are small differences, but it turns out these facilities we have here in Akimov, this one is way more, top one is way more robust than bottom one. It's really hard to mess with the holes around here. But we're in Texas, so we don't really want these boring structures. We want something which looks like alligator tail. So we added more holes outside of our cavities, made it look like this. And what it gives us, why we want to do that? Well, that's because it turns out that if we add more holes on the outside, we increase in reflectivity per hole. So basically, if you have red mirror, you can calculate reflectivity of a mirror as a kind of number of mirrors times reflectivity per hole. It turns out if you do it right, if you add holes like this, you increase reflectivity per hole by a factor of 2, and you don't really lose anything else. Turns out it matters how you add it. So if you do it the other way, if you do it like parallel to the central holes, you do have some increase in reflectivity, but it's becoming more sensitive to parameters, and then at the end of the day, doesn't really give you much of the need. And with this, we can build our cavities shorter, having same Q factor, or have bigger Q factor if we have same size of the cavity. In a theory, we calculated here in Texas A&M that we can get about 10 to the 8 with still having 100% transmission. This is, of course, theory. So in theory, we don't really account that much on a fabricational uncertainty, but in principle, design itself, from material point of view, allows us really huge Q factors. Now, to do it in practice, we went in Agifab. and we just made these cavities. This is standard lithography, so we do spin coat some photoresist on top of it. We cut it, and that's actual pictures made in our in an Akimov, which we have in our lab. And to analyze these cavities, we need to approach them somehow. So what we do, we use tapered fibers, which we also do in Akimov, and we tape also our cavities. So general idea, if you tape two structures and connect them, you hope that mode will go from one structure to another through this tape. And if you do simulation, you can see that you basically can transmit 100% from one to another if you're doing it right. If your angle is right, this overlap is right, and so on. Of course, the problem with this structure is that it's tapered, so nothing is supporting your cavity. So idea was that we will not do that. We will actually continue our cavity, make support. And Abdurrahman, who was student here, he said we need to add small triangle here to block propagation of the light in a cavity. We decided that it's a great idea. We published it. We made all the simulations. We did this in a lab, and we figured out that this triangle doing actually nothing. It actually perfectly fine transmits from one to another, even without this triangle, and with this support. In practice, it works better than you would expect. It just goes where you want it. So technically, the way how we etch in our fibers, we just deepen them in HF. HF is very nice acid which can dissolve your bonds. So please be careful when you handle it. But it also dissolves glass. And that's why we're using this specific acid. So you just deep fiber in it, and you basically pulling it out slowly, and it's becoming thick. Very simple technology. It actually wasn't developed by us. It was developed for scanning microscopes, like near field microscopes. They designed this thing for that, and we just pick it up and are using it for our. And then with a simple setup, which is looking approximately like this. So you have bunch of beam splitters, some detectors, you launch some light, and you can measure what is the efficiency, what is the coupling from your light into the cavity. And it turns out that what we measured is about 96%. A calculated thing for the same structure is 98. It's even within error bar of what we calculated. So it's pretty good. So we can now analyze our cavities. We did some analysis of Q factor of our cavities, and we figured that we experimentally can see Q factor right now of about 24 thousandths, which is of course not 10 to the 8, but this is great for making some strong coupling regime with a germanium vacancy code. So now, what kind of diamonds do we want to use? So there are two approaches. So there are actually two ways how you can grow diamond. One is chemically, you can basically grow it from a vapor if you have some diamond seed and put it in a proper conditions in a vapor which contain carbon, something like methane. Diamond will just grow. It has not very high temperature, around 300 degrees C actually, and not too high pressure. It grows. But more traditional way of growing diamond is compress some powder of carbon-containing material at really high pressure and high temperature. And it turns out that it works better if you use organic compounds, so basically some organics, and then you don't need as high pressure and still much less temperature, and still diamond grows, but it grows with no strain. Normally, when you grow diamond chemically or any other artificial diamond, it has one big disadvantage. It has huge strain in it, which creates some troubles when you handle it. If you're doing it with some organic powders, then you can actually get strainless diamond, and that's what our collaborators in Troyes near Moscow doing. So we like them very much because they supply us with these nice diamonds of various size with germanium vacancy color centers. And that's how these diamonds look like. So it's just like a small powder, which we can then use. This is TEM image of this diamond. So we can see diamond doesn't really look like on a jeweler shop. It's actually something messy, but it's still quite nice. nanoparticles which one can use. And we can have them as small as a few nanometers, maybe up to 10 nanometers. And if we work really hard, we can get even 5 nanometers on average. Here in Texas A&M, we also grow some diamonds. That's not my group, it's group of Professor Hammer, with whom we collaborating a lot. And what he does, he goes one step further. He's saying, look, I can take a molecule which looks already like a diamond, something like this, and I can modify this molecule and put the atom which I want to be my color center, and then grow starting from this molecule. And then what I hope to have is I hope to have just one color center of specific time right in the center of my diamond. And he did the experiment, he and Texas A&M, and it did work. He did it with a nitrogen vacancy color centers, and he did see some nitrogen color centers emission. Of course, there are some problems. As I said, nitrogen vacancy color center is negatively charged, but if you grow it as precisely, you don't have any source of extra electrons, because you have exactly one color center in the center, no source of electrons. Right? So this is still work in progress, and another problem with this method is that he using really small high pressure, high temperature setup around here, and he grows just some nanograms of these diamonds, which he uses for analysis of these diamonds. We have not seen any single one in our lab yet, but they're working on making more massive production of those, and hopefully these diamonds with the color centers in each diamond with some correction on electrical charges state and stuff like that will be soon in our lab. Now, how we position in these diamonds? So we just using lithography, we put in some resist, making holes in this resist and putting diamonds. We have some tricks with hard mask also it's just like for technical reasons, place some diamonds. Sometimes we put some glue. Turns out that many substrates do not really need this glue. Depends a little bit on what you're doing. And then after we removing all these layers of resist, we can see our diamonds in a position where we want them. This method was not developed by us, it's actually developed by other group. Somehow when we tried to copy this recipe, it just didn't work. We spent several months to make it work. Eventually we did. And then that was done in my time in Moscow, and then I moved here and I said, guys, so this is a recipe, so let's do it here and again. And we again spent several months to make it work here, but it does work now, and it works not perfect, but it works good enough for our purposes, because when we position our diamonds in some targets, here it's just like target, we see that in approximately 40% cases, we actually see a single diamond sitting in a hole where we want it to be. In some places, we have some strange agglomeration, like here it's like specifically bad case. It's like really diamonds are everywhere, so something didn't work well. In some cases, we have empty targets, so there is some balance, but for research purposes, we think 40% is good enough. And in principle, it should be possible to optimize it to something as close as 100%. Now, I said I started from a statement that germanium color center is good because it's not sensitive to environment, right? So it's very natural to think about using it for scientific applications. And that's what we did. So we actually got motivation again from Texas A&M. So in biology, there is a problem with measuring temperature on a scale of one cell or maybe few cells. There are plenty of thermometers. Everybody, especially this time, can measure his temperature every day with just like this size thermometer. But when you go down to the size of the cells, there's not that many thermometers. There are actually some. They're mostly poison or destructive. They kill yourself after the measurement. So that's something people start to work on. And again, Harvard was the first. They developed nitrogen vacancy-based thermometer, which can measure temperature down to millikelvin in the size of single cell. And that's great. And in Texas A&M, it was developed further, and these diamonds were placed on a fiber with a microwave emitter supplied, because you need microwave to manipulate state of nitrogen. And it was used to discover how thermal sensation works in a snakes, in some Texas snakes. And that was kind of big breakthrough in biology. But the problem is, this sensor, it actually used few watts of microwave power and approximately microwave frequency, like microwave Fogon frequency. So it basically like cooking while measuring. And I asked Alexey, who did this experiment, like how you actually did it. He said that was very, so they were very careful, playing a lot, with how they can position everything and make sure that nothing is getting cooked. But they are not ready to do this kind of experiment every time. They really need something which doesn't have this microwave. They need some sensor which can measure temperature with some microscale or maybe even nanoscale resolution, but without huge power sources. So we decided we want to do something on optical, and the idea was simple. We can take this germanium vacancy color center and look at its spectrum. So we can measure, and that's experimental data, which was done by these two students, both already graduated. I don't know why students have this nasty property to graduate, but everybody who did something good graduated. So they measured that when you decrease the temperature, increase the temperature, spectral line just shifts. It's not huge shift. It's really hard to see on this plot, but it's measurable. And if you look at this in more details, well, why it shifts? It should not supposed to be sensitive to anything. Well, it's still, it's a color center in a diamond structure. It's still sensitive to phonons, to mechanical deformation of this thing. There is nothing you can do about it. It's just like connected physically to the mechanical deformation. And what these phonons do, they actually induce transitions between states. You can think that that's maybe something resonant, but well, for resonance, you don't have that many resonant phonons. Actually, cross-section is not that great. But for Raman-like process, where you use two phonons from a spectrum, you have plenty of these phonons at room temperature, and they create quite strong process, which create basically something similar to stack shift, shifts your level because of this interaction. And it turns out that from a theory, it should be cubical dependence. We did check it, we fitted our data with the different powers and figured that it's indeed cubical. So we know that we understand the mechanism. And that means that we can actually, by the shift, measure the temperature. We did experiment. We did it at room temperature. We figured out that we can do sensitivity below 0.1 Kelvin. More specifically, it's 300 millikelvins per square root hertz, and it's actually short noise limited, so it's really limited by number of photons we have. Well, because there is nothing on this device, like just spectrometer and your color center, and there's basically nothing else. So there is not much sources of noise. And then we started to work, started to develop. First thing, we started to try to understand what is the optimal concentration of the germanium color centers, what other things we can optimize. We started to scan fiber around our diamond and look how good of thermometer we can make, basically targeting onto the fiber. And we figured that actually original idea of measuring shift of the spectral line was not that great idea, because spectral line shifts because of different things, not only temperature. If you have strain on diamond, it also shifts. And it turns out that if you have this bulk diamond, even if it's very nicely grown diamond, you still have some strain gradient. And when you change, measure change in position, you can see these small breaks in a line where you move to different spot and your sensitivity changes suddenly. Like shit. That's not very good, but what we figured that if you instead measure width of the line, that one doesn't have this extra sensitivity to the strain. It actually turns out to be sensitive only to temperature, and you don't have any other things. So we actually switched from measuring position to measuring width, and that apparently is more universal way, which actually doesn't require any calibration each time. You can just like take a random diamond containing this germanium vacancy pose, and you just get in the same sensitivity. You don't have any additional offset. And again, we measured accuracy and resolution, and it's all slowly getting better, but still about the same. It's below 0.1 millikelvin. And then we decided, okay, so our goal is actually to make a sensor. So we need to put micro diamond on a fiber, and start to scan this diamond around sensor. Then so we ordered some diamonds, put them on a fiber, and we first thing we figured that one diamond is small and it's sitting there on top of the fiber, and to send in some light, and it is actually starting to absorb this light. It's kind of works, it absorbs light, it re-emits, and we measure in spectrum, right? But it doesn't really emit same energy of photons. It absorbs green by 32 and it emits 602. So there's about a little less than 100 nanometers which goes somewhere. It actually goes in heat in a diamond. And if your diamond is micron size and you're trying to put some tens of milliwatts of light power in this diamond, it heats up. So what kind of thermometer is it if you, while you're getting a really good signal to noise, you're getting 50 degrees change. Right? You want to go with 0.1 degree resolution, but you can heat up your diamond on a 50 degree. That doesn't sound good, right? It sounds like you've got a problem. Solution was simple, so I was collaborating with Alexey from this, and he said, well, you use wrong fiber. You should use photonic crystal. You know, we started with photonic crystals. There are photonic crystals again. Photonic crystal fiber, which is designed so that it has high numerical efficiency, so you will collect more light. You will need to use less power, and you will not have this heating effect. We did that in a lab, and what we figured that indeed, if we go to very low power with this photonic crystal fiber, we still have very nice signal to noise ratio, about 20 dB, where we don't have any noticeable heat at least in one scale, in a scale of few factors, which just doesn't heat up and it still melts. And even with this low power, we still getting somewhere around 1 millikelvin resolution because we just now collecting more light. So instead of using more power, we just collect more and excite less, and we're getting same sensitivity, but now we don't have this self-heating effect, and we actually have ideal sensor which can measure this below 0.1 Kelvin resolution, which is more than enough for all this biological application. You can scan it around and you can do the measurement. And the last, and we did some measurements on the wires, just scan this sensor over different wires and measured basically like heat which is produced by Oslo. And then we started to talk, mostly Alexey already started to talk with these biology people, and they said, well, you need spectrometer, that's complicated. Okay, so then you don't need spectrometer. You can just use color glasses and separate your signal on 2 different wavelengths corresponding to 2 different emission parts of your silicon color center. Use something like CCD, or you probably can just use photodetector if you want, and just divide one by another, and you still getting good sensitivity, still below 1 Kelvin, and you still can do your measurements, but now without even spectrometer. So now I want to switch gears. Do I have time still? I should have another 10-15 minutes, I think, and talk about something completely different. Also about quantum, but not related to diamonds at all. It's quantum simulation with Thule metals. Idea is still motivated by quantum technologists. We want to be able to solve some problems which are in current situation and solid state physics they do not necessarily know how to solve. One of the examples is high temperature superconductivity. So we know it exists. We have some models which explain why it may exist. We don't have any model, as far as I know, I'm not a theoretician, any model with prediction power, so we don't really know how to construct high temperature superconductivity. And people want those, so we need some instrument how to predict how to make this kind of high temperature superconductor. But something in other which may be interesting. So another example is magnetic material. So magnet seems to be, we know about magnets. I actually don't know for how long, but definitely over 2,000 years. But quantum mechanical description of magnets turns out to be tricky, because even if you take some simple system of 3 magnetic atoms and trying to form a triangle out of them, if you're trying to flip one of the atoms, you actually don't know which one to flip, because whatever you do, like 2 will try to flip each other, and once they flip, the other 2 will try to flip each other. So there's always one conflicting bond here. So you have kind of something which is called frustrated magnet, something where ground state is really hard to find, and that's only 3 atoms. If you do more, situations quickly become really hard to compute. So Richard Feynman a while ago said that if you have a situation when you don't know how to compute something, you should not, you instead should model it. So you should build quantum mechanical system which has same Hamiltonian as one you study, or at least very similar one, but which you can control, in which you have handles and can change all the parameters, and better this system be evolving on a human time scale, not on other second time scale, so you can actually watch what's going on, and then you can watch what's happening, tune parameters, and maybe build some theoretical model to understand it, or maybe just like try to tune these parameters so that you achieve the result you want, or better do both. Right? So you tune it, you see how the system reacts, you talk with theoreticians, they develop a model. Based on their model, you make new approximation, and this way, together, one can build and first understand materials and then build some new materials. It turns out that this kind of approach doesn't necessarily apply only to materials. You can try to simulate something like turbulence in atmosphere. You can try to understand nuclear interactions. You can try to understand how universe began and try to model Big Bang. It all depends upon how, what kind of Hamiltonian can you build and what kind of interaction you want to model. So in our specific case, we're trying to use cold atoms, and cold atoms, if you put them in an optical lattice, they see potential, which is like periodic, which has some, potential wells, and it looks like what electrons see as a crystal field produced in some matrix, right? Of course, it depends a little bit on which task you're solving, but on this example, you can see that if you just cross a couple of laser beams and put atoms in the maximum of these laser beams, they will be having lattice which is similar to what electrons see in a solid state, and this way you can model transport properties of this electron. You can also look at this system differently, and you can make each atom sitting in a lattice magnetic, and then you can see, say, transition of ferromagnet to antiferromagnet or model magnetic interaction, because now they are magnetic, but they are in well-defined position. You can maybe look at each of them, and then you can understand what happens, how phase transition happens, how magnetization happens, and answer on all these complicated questions. So question is, which atom is the best for this kind of simulation? The answer is, of course, there is no atom which is the best. It depends on your application. But there are atoms which are interesting. So if, for example, we look at the bottom of Mendeleev table in this red line, these atoms have F electrons in their shell, and that's making them interesting because F electrons are responsible for some interesting properties. So we decided to work in this field, and we picked thulium. There is a couple more atoms in this row which also got cooled down. Ytterbium is the very first one which was cooled down to BC temperatures, but this one, Bose-Einstein condensation temperatures, I'm sorry, has full F electron shell, so it's already all 14 electrons are there, and that means it doesn't really have any extra properties related to electrons. It's more or less alkali atom. It really has basically 2 s electrons on outside, so that's what defines its properties. But two other guys, dysprosium and erbium, they have not completely filled F shells. They have some holes in those, and those atoms are magnetic because F electron has large magnetic moment associated with this, and dysprosium has about 10 Bohr meters, erbium has about 7 Bohr meters. We picked thulium. It also has large magnetic moment. It's 4 Bohr magnetons in the ground state, but it has much simpler level structures than these two guys. And that's these two guys were working on 1 micron dipole trap because they wanted to be far away from a transition. We were able to work in a 532 nanometers dipole trap, like make these atoms closer to each other and still get Bose-Einstein condensation. So there are a couple of things one need to know to do this quantum simulation. So one, how we can actually tune interaction between atoms, right? If there is no knob, there is no point of doing anything, you need to be able to change the way atom interacts. And the knob is so-called flashback resonances. So what happens if two atoms are colliding? They could be seen as molecule, right? You can draw molecular potential for these two colliding atoms, which would be something like this. And then depending on what is the distance between like trajectories of these two atoms, you can associate different angular momentum with these atoms. And once we go to quantum mechanical levels, this momentum is of course quantized. So we can have 0, 2, 4, 6, and so on. We cannot have 1, 2, 3 because of the symmetry. We have bosons in the system, and they cannot have antisymmetric wave functions. But we can have symmetric functions. And then once we go to some orbital momentum which is bigger than 0, we actually have this fictitious, in a sense, but very real from point of view of atoms potential, which is called centrifugal potential, which is just like a fact that reflecting fact that they have non-zero distance between them. So if we reduce the temperature, then all collisions which have this barrier usually go away, and what we're left on is this kind of potential where atoms are colliding more or less freely without any barrier among them, but atoms have another degree of freedom. So we usually like have all the atoms prepared in one specific magnetic state, but in the presence of a magnetic field, if there is another possible state, we can draw another potential in which atom, of course, cannot be, because in this case it happens to be high in energy. You cannot be in a free state and be below bound potential level here. But as atoms approach each other and them shortens, they can actually see levels from this other possible configuration of the same atom. And they can tunnel this level, especially if they're in resonance with this level, and come back from there, and that will enhance collision probability. So it turns out with this simple mechanism, you can turn torsion cross-section anywhere from -infinity to +infinity. Now, of course, there is a trick. So once your absorption cross-section becomes large, then you actually starting to see three-body process and two-body process when atoms are colliding to conserve energy and momentum. They cannot be in a bounded state as a result. But if it's three or more atoms, they can, and you're starting to see losses from your trap when your scattering length becomes too large in absolute memory. And those resonances can be observed, so you can observe this kind of losses, and then you can tune somewhere outside of three-body collisions, and there you have plenty of tunability to change cross-section, your interaction between atoms. So thulium atom has F electrons. F electrons happen to be responsible for this kind of Banach-Fishbach resonances, and we can observe plenty of those at all fields. So in fields that few Gauss, we have something like, I don't know, 15 resonances of different fields. So plenty of tunability. It's still much less than an erbium and dysprosium. Their resonances are just, like sitting on top of each other, but we treat it as a better tunability. You can actually find the isolated ones and really tune your scattering lengths carefully, not really mess with, overlapping resonances. And compared to alkali atoms, in alkali atoms, pure Fishbach resonance happen in a field of 700 Gauss. Much higher fields, they're much more rare and much more difficult. Here, everything happens in really small sizes. Now, it turns out that for quantum simulation, your first step where you need to start is Bose-Einstein condensation. What is Bose-Einstein condensation? If we cool down atomic gas, at some moment when temperature is low enough and density is high enough, all atoms in the ground motional state of this system, and they starting to behave as a one object, as a one wave, one classical wave. So this basically happens when the distance between atoms becomes comparable with the de Broglie wave. So then wave properties of the particles start to dominate, and they start to behave all as a classical wave. And we like it because this is one state for all atoms. So if you want to do some simulation, you need to know where you are to begin with, right? You also don't want temperature reading in the system if you want to do simulation, because you want your atoms to be kind of controlled and not have. So Bose-Einstein condensation basically is the initial state for any quantum simulator. So we need to reach it for thulium, but the problem is thulium is a metal, and I didn't find really phase diagram for thulium, but like for iron, it's on Wikipedia. If you look what happens if you got vapor of some metal and you just cool it down, you can go to the lab, put it in a liquid helium, and say, oh, now we'll Bose-Einstein condensation. It would not, because if you just go down in temperature, you meet metal state. And if you just cool it down, it will transform to metal. It will not go to Bose-Einstein condensation. Right? If it can, it will do metal. So you need to be very careful on how you do it. You probably want to go to as low pressures as you want, and you want to control your collisions and try to avoid free-body recombination and avoid formation of metal. It turns out that nevertheless you do need collisions. You want to avoid them, but you do need them because that's the most efficient way of how you cool atoms. So the way how you cool atoms called evaporation cooling. So you basically have atoms in some kind of trap, and you let atom collide, and then some atoms, the result of collision, will have very high energy. And if your trap has finite depth, they will escape. The rest of the atoms will thermalize, and they will see less energy left. Like high energy went away, those who left have less energy. And it turns out to be the most efficient mechanism. And it sounds simple, but in order to do an experiment, what you need to do, you need to load atoms in magnetic optical trap, then reload an optical dipole trap. And optical dipole trap is much smaller than magnetic optical trap, so you need somehow to increase size of this optical dipole trap. So you might do it by scanning, and then you need to compress it back because you want high density, and you need somehow to reach these low temperatures and still high enough density for the condensation to happen. And you also need somehow to ramp down amplitude of your trap, and that's essential because you want atom to leave fast enough from a trap so they cool down. And if you do just one dipole trap, what happens? Your atom becomes really delocalized in one direction. You want to compress them, so you add in another trap, but again, you decrease in size. You don't want it to happen too fast. You want it to collect all these atoms. And question is how you optimize all these steps. So one way of optimization, you've given a student a task saying like optimize. And student thinks year, another year, and he gets nothing. Trying to optimize this efficiency of cooling on each step, and it just doesn't work. Another way, you remove a student and you put in computer instead of the student, and that happens to be more efficient. So, and the story behind this, I actually went on one conference, Olga Kocherovka invited me on, and I heard a talk about people using machine learning to improve magneto-optical trap. And I'm like, they can improve magneto-optical trap, and they did by order of magnitude by using computer instead of like hand adjustment. Magneto-optical trap is like well developed, everybody knows how to do it. Turns out there is extra order of magnitude out there. Why can't we use it for cooling down to Bose-Einstein temperature? I came in the lab, talked to my student and said, look, can we use machine learning? He said, oh, for the first time you said something clever. Okay, I will do it. So he did it. He programmed computer to control entire setup, collect, set some parameters in the setup, collect images from a setup, estimate temperature and density of the gas, and do it again. And that's basically how it was looking. So first, machine was doing some random steps, and then at some moment after enough of random attempts, some learning mechanism, Gaussian learning mechanism was turned on, and that was optimizing basically efficiency of evaporation. That was phase space density normalized on a relative loss in number of atoms. And by letting machine optimize this parameter, we figured that we can optimize this parameter from something which was like 1.5, 1.7. 1.7 was achieved only by one student, the rest was using 1.5. To something like 2.2. And that's the difference between having Bose-Einstein condensation and don't have it. And if one look in the trajectories, one could see that phase span density has some kind of funny jumps here and there. It's not like it's something like completely crazy, But it turns out when you have a student in a lab, he trying to optimize on every step and don't have this, horizontal line here, horizontal line there. They trying to do it like uniformly, and computers say that's not the right way to do it. So we do have perhaps in the condensation of thulium right now. Alexey is already standing, so I'm probably out of time, but I'm also out of slides either. So this condensation we can see by special shape of the cloud. We also check our sequence on a different magnetic field. We tuned a little bit scattering lines and measured, and we figured that our sequence is actually working like it is in many different interaction strands. So it's quite robust. We check that it's potential condensation because we not only see this cloud, we also let this cloud expand. And if this cloud pattern behaves like a wave, it also should diffract like a wave. It should expand like a laser beam when it compressed in one direction. More, it should expand more in this direction. And that's indeed what we see, and it does expand more in one direction than in another. And if you do it with thermal cloud, it just expands proportionally. And here I'm coming to my conclusions. So we working a lot with the diamonds, not only with diamonds, also with quantum dots here. We're trying to build quantum optical devices with single photons. We're working on applications of our thermometer, and we're also planning to do some quantum simulations with the cold atoms. So here are my current students working in the lab. Shafan doing basically everything. Mahit working on a photonic crystal parity project. Shina working mostly on a quantum dots, which we're not talking about. I collaborate a lot with Stuart Hammer, Alexey Zheltkov, and Olga Kocherovskaya, and there is some of the students as well. And there is plenty of guys who already graduated but were involved in a project in different types. So this last couple of guys are undergraduate students, which we will not in the last graduate students. Thank you for your attention.
Thank you, Alexey. Let's see, do we have questions? Anyone online wants to ask a question, raise your hand, and let's use your microphone so that people in the audience can hear it.
Yeah, hi, Alexey. I have a question. Rupak Mahapatra here.
Go ahead.
Yeah, so I was wondering, have you considered ion implantation instead of synthesizing this? I wasn't sure when you showed the fabrication in AgiFab, how controlled those color centers would be. Have you done any, have you shown how uniform they are? And if those are single emitters?
The question is if we consider implementation instead of condition this color center.
I can't hear.
Another question is if we check if they single photon emitters. So we did check if they single photon emitters. That's actually quite easy. So you split emission on two channels and you have single photon counting device and you measure correlation between those two. So if you have enough proper electronics, it's straightforward. Those are single photon emitters. So did we consider implantation? Yes, we did. And we're still considering it. That's also a possibility. So implantation creates quite some damage in a diamond. So in terms of coherent properties, diamond is better if it is as grown color center compared to implanted one. But in principle, if something like goes off with a yield or something, we can always switch to implantation.
Trying to see.
And also, I just want to mention, if this, once this is a controlled process, so this could be used as a particle detector, right?
We didn't understand, Rupak. What's the question?
You could use this as a particle detector, a dark matter detector.
Particle detector.
Right.
I'm trying to see if there are questions through chat. Rainer, do you
I've not
see
seen
any?
anything. No, I've not seen anything in the chat.
Oh, okay, good. Any questions in the audience here? Yes, Peter.
Yeah, so it's very simple. So you take
Alexey, could you please repeat the question?
So summary of the question is how can you build Feynman ideas, this quantum simulator, out of thulium atoms? So basically, you're taking several lasers, create an optical lasers you want to see, then you take about same condensation of thulium, putting it into this optical lattice, then you tune your magnetic field so that you make interaction between atoms you want, and you tune depth of your optical thread so that you like it. You're starting them to change spacing in atoms, interaction between them, and starting to measure transfer of your atoms through this lattice and trying to see when you have superconductivity. Yeah. So Peter is saying that lattice, which are actual high temperature superconductors, have very complicated, and how you can actually model it with some simple optical lattice. The answer is, well, that's difficult. So you need to have many lasers to simulate that, and nobody have done that yet. But people are working in this direction. They basically increase the level of complexity, like layer by layer. So first people started with just two-dimensional things. Now they add another layer. So we have now 2 layers systems, and target is, get there eventually. But that's not going to happen tomorrow. It's going to happen in some time.
Okay, any other questions? Anyone wants to ask a question online?
I have one more quick question. It won't take long.
Rubak has one more question.
Yeah, so
Yes,
I'm
just a
very
second.
excited
Let me
hearing about
put
this.
the microphone here. Just a second. Go ahead.
Yeah, so I was thinking about the silicon vacancy color centers instead of germanium. I mean, of course, your needs are that the spin phonon coupling would be much faster in silicon. Maybe that's why you don't like it from a quantum computing point of view. But if we were to consider particle detector, that fast coupling could be useful. What do you think, Alexey?
Well, we certainly can. It's possible. It depends on the problem you solve. So maybe for particle detection, silicon is better. We can talk about it. It's absolutely possible that it's useful in some situations.
Okay, thank you.
Okay, let's wrap it up and thank Alexey one more time.
Hello.
Thank you.
I think Valerie
And
has a question.
thank you all the participants. Oh, Valerie, do you have a question?
Yeah, I have a question.
Yeah, we can continue the discussion here as people feel free to leave.
Okay.
Go ahead. Ask your question.
So my question is, how do you observe and what do you observe for as Bose-Einstein condensation of atoms?
The question
Could you say it again? We missed something in the beginning of your question.
That we observed Bose-Einstein condensation of atoms. Correct?
Yes.
Yes. So what did you observe? So how it is, how it manifests itself?
Several things. So we observed distribution of atoms when we let a cloud expands. Its distribution with parabolic shape plus Gaussian shape, which manifest on a possible Bose-Einstein condensation. Of course, it also could happen if you have like a hydraulic regime of expansion, but that we tested by calculating Knudsen number. Knudsen number is not kind of manifesting about any like problem with having strong interaction between atoms. So we see that that should be Bose-Einstein condensation. We also measured how a cloud expands versus time, and we see that where cloud was compressed, it actually expands faster compared to the other direction. And we also measured, I didn't show this slide, but we measured how critical temperature of condensation depends on density of atoms. And that matches reasonably well to the Quasi-Einstein condensation theory.
And to Pareto's shot, or no, what is dimensionality in your case?
What is?
I'm sorry, say it again. You're asking about the directionality.
What is the dimensionality? It is 2, 3, 1.
Dimensionality.
Yeah, so this is three-dimensional condensate.
Two
So we
dimensions.
didn't really try to reduce dimensions or anything, so this is just three-dimensional.
Mm-hmm. 3 dimensions. Okay. It's probably more. Thank you.
Okay, thank you, Valerie.
Then I think we can turn it off. Huh?
Yes. Rainer, can we go ahead and turn this off?
Yes, sure. All right. Thank you.